Hello everyone. In this part of the video, I'm going to show you how to build a fully procedural, physically based eye shader in Unreal Engine. Starting from a refracted camera ray system, then creating a dynamic iris UV setup with pupil control, and finally assembling everything into a production quality eye material. This system gives you realistic iris depth, proper refraction, controllable pupil dilation, and physically accurate color blending all inside a single material. First, create a new material. Then open and import the iris texture. Keep its compression and sRGB setting as default. Then connect it to the base color. Alright, so before we jump into textures and all the fancy stuff, we first need to build the core of the eye shader, the refraction-based parallax system. This is what actually gives the eye its depth and makes the iris feels like it's sitting inside the eyeball instead of being just a flat texture. First, we will take the camera vector and the vertex normal nodes. Then invert them by multiplying them by -1. Then we will expose an IOR parameter and we will set its default value to 1.33, which matches the physical refraction of the human eye. Then we will divide 1.0003 by this IOR value. This gives us the refraction ratio used to bend the camera vector. These two inverted vectors then go into a dot product which calculates the angle between the view direction and the surface of the eye. Then multiply the inverted camera vector by the IOR divide node. The dot value is then passed through multiple power and 1 minus nodes. This reshapes the fall-off curve and creates a physically correct refraction profile. Now we reconstruct the refracted vector using a series of multiply, 1 minus, and square root nodes. This block implements the mathematical form of Snell's law directly within the material graph. The square root calculates transmitted component of the ray, and the subsequent math combines it with the surface normal and the view direction. Multiply the output of the dot product by the result of the divide node, and we combine the viewing angle information with the refraction strength. This gives us a clean, controllable refraction factor that reacts correctly as the camera moves around the eye. This multiply and square root node is fed into the subtract node, where it's offset against the base refraction value. This gives us a controlled way to redistribute the refraction intensity, keeping the center of the eye stable, while gradually increasing distortion toward the edges. Multiply the subtract node by the vertex normal. This makes the distortion naturally increase toward the edges of the cornea and remain stable near the center, exactly how real eye refraction behaves. Feed both of these multiply nodes into the add node to combine their contributions into one final refracted ray. After the final add and multiply operations, we multiply the whole result by -1 and end up with a clean refracted direction vector. This vector represents the actual direction light travels inside the eyeball after bending through the cornea. This refracted ray is what we'll use to drive the iris UVs and create real optical depth in the eye. Now that we have our refracted ray, we will use it to drive the iris UVs. We start by sampling this normal texture, keep its compression and sRGB setting as default. Add a radial gradient exponential, we will use it later. Then add a constant 3 vector and change its color to red. Transform the normal and the constant vector from tangent space into world space using a transform vector node. Both of these vectors are then normalized to ensure all following math stays physically correct and stable. Next, we compute the dot product between the normalized normal vector and the normalized direction vector. This tells us how directly the surface is facing the camera, which is the foundation of all optical shading. We multiply the dot result to control the strength of the effect. Then subtract the two results. This subtraction creates a directional offset that simulates the bending of light as it passes through the curved cornea. The result is then normalized again to keep the distortion smooth and artifact free. Then we generate a perpendicular direction using a cross product, which helps us build a complete 2D UV offset from the 3D refraction vector. Next, we project the refraction vector into UV space by taking dot products against the surface's tangent axis. The output of this dot node is then multiplied by itself. After that, we feed this into a lerp node with values 0.3 and 1, so the effect never becomes too flat or too extreme. Take the final multiply output from the refracted camera ray setup and connect it directly into this dot product of the normalized normal vector. We will generate the actual iris shape using this radial gradient exponential node later. Now we will add depth. For that, we will create a scalar parameter called iris depth with a default value of around 0.2. This controls how deep the iris appears behind the cornea. We multiply the output of the radial gradient node by this iris depth value. Then we pass this result through the A of a divide node, and in its B, we plug in the alpha of this lerp, which comes directly from the normal texture. This means the normal detail smoothly fades in only where the iris exists, with physically correct depth falloff from center to edge. Pass this result through the B of a multiply node. From the refracted camera ray section, we take the output of the final multiply node and plug that output directly into the A of this multiply node. So, instead of the iris depth being a flat procedural effect, it is now driven by the actual refraction of the camera ray. Then, we will take the final multiply output of iris depth and plug it into the A of the both dot nodes in the iris UV section. These two dot products rebuild a new UV coordinate system that curves and compresses the normal map exactly where the iris sinks into the eyeball. We combine them using MakeFloat 2, forming a proper 2D UV offset. This offset is multiplied by a -1 and 1 constant vector to flip the horizontal direction, so the distortion moves correctly with the camera. Then, we multiply again by the refraction depth scale parameter, which controls how deep the iris appears beneath the cornea. Change its default value to 0.3. We take the base UVs from text code and add the refracted offset to them. Create a divide node and connect to the radial gradient node that we created before. Then we create a scalar parameter with 0.2 as its value and name it iris diameter. This parameter controls how large or small the iris appears. Run this through this divide node. This recenters and scales the UV space so the gradient remains perfectly circular and centered on the eye. Then again, we will add a divide node and plug the iris diameter directly into its B. The reason for this divide is to normalize the diameter value. To scale the iris around its center, instead of the top left corner, we shift the UVs by subtracting it with 0.5. Pass the result through a multiply node. Then, we will take the output of that divide node and connect it directly into this multiply node. This multiply node is controlling how strongly the refraction and parallax offset affect the iris texture coordinates. Add 0.5 back to return the UVs into normal texture space. Then subtract 0.5 back to keep all transformations centered on the iris. Next, we normalize the vector to ensure consistent directional behavior regardless of texture resolution or UV density. The normalized direction is then multiplied by 0.5. This compresses the UV direction into iris space, ensuring our textures stay perfectly inside the iris boundary and don't stretch at the edges. Using the vector length node, we calculate the distance of each pixel from the center of the iris. We amplify this distance by multiplying it by 2, then invert it using a 1- node. This converts the radial gradient into a soft circular mask. The mask is then multiplied by the pupil scale parameter, allowing real-time control over pupil dilation. Change its value to 0.9. We will use a lerp node to blend between these two states. A is our compressed iris direction. B is a constant 0, 0 vector representing the pupil center, and the alpha of this lerp is driven by our pupil dilation math. So the closer a pixel is to the pupil, the more it collapses toward the center. Finally, after all the distortion math is complete, we add 0.5 back to the result. This converts our iris UVs from centered space back into standard UV space, so they can correctly sample all of our iris textures. The output of this block is our final iris UVs, which is connected to the UVs of our iris texture. Now that the iris UV system is complete, the next step is to generate the final iris mask. For that, we will multiply the radial gradient node, which we created before, by a new scalar parameter called iris edge sharpness. Change its default value to 5. Finally, we will pass everything through a saturate node, which clamps the mask between 0 and 1 and gives us a clean iris mask. This output is now our final iris mask. Now that iris UV system and the final iris mask are complete, the last step is to assemble the actual eye color. For that, we will create a lerp node. Into its input A, we will plug the sclera texture, keep its compression and sRGB setting as default. Into its input B, we will plug the iris texture, and for the alpha, we will use the final iris mask that we just created. This lerp blends the sclera and iris using the physically correct iris shape, so the iris appears exactly where it should and fades naturally into the white of the eye. Finally, we will connect the output of this lerp directly to the base color of the material. And now we have a fully procedural eye material. Create and open its material instance. And let's check it. Here we'll add a slider min and max for the iris diameter. Lastly, we will arrange the nodes using comment boxes and save the material. And with that, this part of the eye shader is complete. In the next part of this tutorial, I'll show you how to create proper scalar parameters for the iris and sclera, how to work with specular, roughness, and normal texture map, and how to add advanced layers like clear coat and fuzz, along with fully adjustable parameters for each of them. If this helped you, make sure to like and subscribe, and I'll see you in the next part.